create our first reliability growth analysis. So we've launched WIWO++, and now we've got the options. Either we go under the Home tab, we go and look for this reliability growth or growth data icon, or we can look for this folder, growth data, and right click, and we add growth data. Now behind this single icon, in reality there are a number of analyses that we can carry out, and they are divided into two categories: developmental type of analysis, or reliability growth, or fielded repairable data, so system repairable data. So we'll be looking at reliability growth analysis in times to failure type of data, but we also have discrete or one-shot system data, or data deriving from a multi-phase system, or reliability data. And lastly, instead, in the category of repairable system, we have a repairable system, it could be more than one system, or we go a fleet analysis. So we said we're going to do a reliability growth. We select the first option and we click OK. And then creates an interface similar to WIWO++. So we got a time to event, and we got the other part is the equivalent of subset ID in WIWO++. So we paste our data, this is our data, and now we want to analyze this data according to a reliability growth model. So for this type of data we have two models. We got a Crow-AMSAA and HPP, or we got a Duan model, which is an empirical model, or in alternatively, but we would need some additional information, we could also use a Crow-extended type model. So for this analysis we'll be looking at using the Crow-AMSAA and HPP, and then we click OK. The parameter calculation is done via MLE, so there's no regression on it, and the confidence bounds are Crow confidence bound. So after we calculate, we basically evaluate the model, and the model has a shape parameter with a beta and a scale parameter with a lambda. And then we got some additional information, which is like the growth data, the demonstrated MTBF, demonstrated failure intensity. And then we've also got some statistical tests with a confidence level, or significant level if we want. And this is, for example, a Kramer-von Mises test, which basically, in this case, is passed, so it's okay. It basically says, is the model, Crow-AMSAA model, suitable to analyze this type of data? And the answer that we got here is okay. So we can have a look at the graph now. We look at the graph, and the first graph, it actually generates three types of graph. The first graph is the cumulative number of failures. So we also got a termination time, termination line, which is the last reading. And that enables us to make a prediction of the number of failure in our system that we'd expect after a certain time. And obviously we can apply confidence level if we want. Or we can look at, for example, a mean life. We're going to modify some of the graph and trying to make it a little bit more readable. So change the scale. Okay. So what we got here, and we also we make it like that. So what we've got here is it shows how the MTBF, which is a variable parameter of our model, changes in time. And we got two curves. We got an instantaneous MTBF, which considers basically a delta t. So is a very small interval that we are considering, as against a cumulative MTBF, which instead takes into account the interval from 0 to the data points it's trying to build. So we've got instantaneous MTBF, and in this case we can see our system is improving and failures are becoming more spread out, if we want. Okay, so there is a growth, if we want, in our system, and the demonstrated MTBF at the end of our reading time, which would be at 6,978, is 978 hours. But we can interrogate our lines more precisely via a QCP, or quick calculation pad. Say we want to interrogate at 3,500 hours, and we can read exactly the value of interest. And that's it. Thank you very much.